Imagine you are standing in front of a locked door with 1 billion keys. Only one key opens it. To find the right one, a traditional computer, even a supercomputer, has to try them one by one. Key 1? No. Key 2? No. Key 3? No. In our course, Parallel Computer Architecture, we learn about making computers faster by adding more brains or cores. But even with 1,000 cores, you are still just trying 1,000 keys at a time. Against 1 billion keys? That is still too slow. This is the fundamental limit of the classical bit, the language of zeros and ones. It forces us to think sequentially. But what if we could try every single key at the exact same instant? Welcome to the world of quantum parallelism. To understand it, we have to rethink the bit. In the classical world, a bit is like a light switch. It is either on or off. But in quantum computing, we use qubits. Think of a qubit like the Earth. A classical bit can only be at the North Pole or the South Pole. But a qubit, thanks to a property called superposition, the qubit can be anywhere on the planet. It can be on the equator, in Saudi Arabia, or in Antarctica. It represents a mixture of 0 and 1 simultaneously. It's not just on or off, it's everything in between. Now, here is where the architecture part gets crazy. If you have 1 qubit, you have 2 states. If you have 2 qubits, you have 4 states. 3 qubits, 8 states. This is exponential growth. By the time you have just 300 qubits, you have more parallel states than there are atoms in the entire observable universe. This creates quantum parallelism. While a classical computer walks through a maze path by path, hitting dead ends and turning back, a quantum computer explores all paths of the maze at once. It doesn't find the answer emerges from the parallelism. But superposition isn't the only tool. We also have entanglement, where qubits become linked instantly, no matter how far apart they are. However, there is a catch: measurement. While calculating, the qubit holds all answers at once, but the moment we look at it, the superposition collapses. It forces the qubit to choose just one state. So how do we make sure it collapses into the right answer and not a random one? This is where the magic happens. The power to say no. Quantum computers are excellent at identifying what doesn't belong. Instead of looking for the one yes, we can manipulate the probabilities to cancel out the billions of no's in the background. We amplify the correct solution so that when we finally measure, the answer is right there. This isn't just theory. As we saw in our course, initiatives right here in Saudi Arabia, at Aramco and our universities are preparing for this revolution. We are moving from simply adding cores to mastering the physics of information. And this is the future of parallel computer architecture.